Welcome to the Picture Language Seminar. We're very pleased today to have Jintai Ding, an expert on post-quantum cryptography. Until recently, Professor Ding was at the University of Cincinnati, but then he moved to Tsinghua University, where he's head of the Ding Lab in privacy and protection, and also at BIMSA, the Beijing Institute for Mathematical Sciences and Applications. Professor Ding is going to tell us about cryptography based on learning with RSA, which was introduced by Oded Redkov in 2005, and Ring learning with RSA introduced by Ding in 2012. So we look forward very much to your talk and learning about this new subject. Professor Ding, why don't you share your screen?
Okay, thank you. Just 1 second. Okay, let me share my screen. And let me do just 1 second. Okay, so is it okay? It's
great.
The screen okay with everyone?
Yes, we see it. And
okay, thank you.
I think that you hope that people will interrupt with questions as you go along.
Yes, you're always welcome. Feel free to interrupt me anytime. Should I start now?
Please start.
Okay, yes. First, again, I would like to thank Jeffrey for the opportunity to speak here. So my name is Jintai Ding. Right now, I'm affiliated with Tsinghua University and BIMSA, Beijing Institute of Mathematical Science and Applications. So today I will talk about post-quantum key exchange based on the LWE problems. Maybe I make a small correction what Jeffrey said earlier. So the LWE was introduced by Oded. Ring-LWE is not introduced by me, but the key exchange I invented based on the LWE problems. Okay, so I assume actually most people here are not experts in the area. So I will give a fairly straightforward, I think, talk, hopefully to give you the basic idea what is happening in this world, namely in modern public key cryptography and then post-quantum cryptography. So I'll start now. Okay. Things I want to talk about modern cryptography. People ask, what is before that? What is traditional cryptography? So in my definition, traditional cryptography is called symmetric cryptography. Namely, in a symmetric cryptography setting, the sender and receiver have exactly the same information. So here I give the simplest example. This is the famous ciphers cipher. And let's pretend they're using English at the time. So this cipher is a very simple mathematical idea. So you have the alphabet arranged in the ring and you rotate it. For example, in this case, the inner ring was rotated by 4 positions. So which means A is correspond to E, B now correspond to F, and so on. So this is clearly a bijection from 26 letters to 26 letters. So when you encrypt the information, you just switch A by E, B by F, C by G, etc. So this is the encryption process. The decryption process is the opposite way, right? You just replace E by A and so on. Yeah, and here the important thing is that this rotation of 4 positions is shared by both sides. So this information is symmetric. Okay, and clearly this is not a very idea in the sense we can guess 26 positions and we easily can break it. And we are mathematicians, and you can imagine a very simple improvement. Instead of doing this rotation, we can do a permutation. So there are 26 factorial permutations, and this one can also easily be broken, especially for English, because in English letters we know the letter with highest frequency is E. So therefore, as long as I intercept enough messages, I can easily figure out which letter is E. And maybe some of you know what's the second letter with what's the letter with the second highest frequency? Can someone give a guess? So I think some of you must know, right? The letter with the second highest frequency.
A.
No, it's T. Yeah, anyway, so and then so on and so on. So this is not so secure, right? Then we can improve further, right? So we can It's a permutation on one letter. We can do permutation on what? 2 letters, even on 3 letters. Yeah, so we can build a table, map this order the 3 letters to another 3 letters. Okay, but as you know that when you do that, if the table is getting bigger and bigger, okay, and it becomes slower, but we are practical people. We want to be fast enough, right? Otherwise, it becomes useless when the tables become too big. And then in modern world, what we do is we use machine to do it. For example, this is in the picture is the famous Enigma machine. And you can see those circular devices. These are so-called routers. They are actually correspond to some kind of permutations. When you turn the routers, that corresponds to the keys. And later, we based on the same principle, we have DES and AES. So AES stands for Advanced Encryption Standards. That's what we use now. Okay, this rotation of the routers and those you can see those guys here. When you rotate, means you choose different keys. Okay, and the basic mathematical idea is the same. You are trying to build a complicated permutation, but you want to do it efficiently. One way is encryption, another way is decryption. But not to do this, the 2 sides must have exactly the same keys. Okay, which means I have to know which position you rotate to, then I can do decryption correspondingly. So this means we must do what is called a prior secure key exchange. Okay, and namely 2 people, if you want to use this machine securely, you must agree beforehand, which means we have to agree on the keys. And this is doable on a small scale. For example, the German U-boats, right? So this means each captain of a German U-boats, before they board their boats, they have to go to headquarters, pick up the key book and decide, and then they can decide which keys they will use. So this is the basic idea. But from a mathematical point of view, this is actually very easy. Namely, we try to build a permutation on the set, on the finite space FQN. This is a vector space of n dimension. And we want to do random permutation on it. So what do? You do compositions of simple permutations. For example, here S1, T1, S2, T2. Okay, so this S1 are efficient nonlinear maps, and T1 are efficient linear maps. We know linear maps actually is very efficient already. And you would ask me, what are the possible efficient nonlinear invertible maps? And the simplest example, this is actually used in what is called DES. It's called the de Jonquière map. This is a map studied very well in algebra geometry. Okay, this map is map T x1 x2, map x1 x2 to x1, and then x2 plus fx1. And the inverse is very easy to compute, right? Just subtract fx1. And these maps are related to Jacobi conjecture, related to a tame map, a wide map, and related to Nagata conjecture. For those of you who know Jacobi conjecture, you know about this. And the fundamental idea you should understand is what? We use simple permutations, compose them to build more complicated permutations. The more you compose, the more random those maps are, and therefore more efficient, more secure they are. But you have to consider efficiency. So deciding how many rounds you do is the key. And also here, you can see easily that by doing this, we can actually build any random maps in principle. Okay, one way we know this is because if you can do two permutations, then you can compose 2 permutations, you achieve any permutations, and this is a very similar idea. Okay, so this is a symmetric cryptography, and those designs are actually very good. Okay, it's very secure. Okay. And then the people, the mathematicians who first start to analyze are actually Polish mathematicians. In 1930, for example, this guy, Maria Brzezinski's already start to analyze it. And later, actually, they passed their knowledge to Turing, who broke the system. Okay, so here maybe I want to tell you an interesting story. Even though we claim Turing broke it, but when Turing built the machine was mostly coming from parts in the US, especially from this place called NCR, which was headquartered in Dayton, Ohio, very near my home before. Okay, National Cash Register. I think Jeffrey, you must know this place, this thing, right? At your age, the cash registers, and you and me know this, right? So, please.
Yes. Go ahead.
Those cash registers. So turns out during the Second World War, Turing often slept on the couch of the CTO of an NCR, and they helped Turing build the machine that's broken the Enigma machine. Okay, and so in the Second World War, many things happened. I mean, for example, U.S. broke Japanese Navy code, and Japanese broke U.S. Army code, and we also heard about the Navajo code talkers. Okay, but all these things, I would like to emphasize that we only heard about it recently, even though the system was broken in 1942, and the movie about Turing, I mean, the imitation game, talk about what he did. Really, we only heard about it very recently. Which means the government keep the secret from us. Okay, but the one reason I mentioned NCR is that at the end of the war, the U.S. Navy went to NCR to talk to them, say, would you like to continue making computers? The NCR people said, no, we will go back to make cash registers. So the joke is that if they agreed, probably Silicon Valley will be in Dayton, Ohio, not in Palo Alto. We don't know, of course. So history is a very interesting topic, I have to say, when I heard the story. Okay, so this is about symmetric crypto systems. Okay, the key issues here, of course, when you think about it, is the trade-off between efficiency and security. So here I would emphasize it again, that the Enigma machine, even now, if you want to break it, is very, very difficult. But Germans made various mistakes, make it easy to break. For example, Germans in the military, when you send a telegram, the first style, Heil Hitler, which means no matter what they do, we know the first few, how to decrease the first few words. And that actually helps a lot to break the system. Okay. And so what I will emphasize is that in order to use this symmetric crypto system, you must do key exchange, and such a system is not scalable. Okay. Yeah. And again, so when people break a system, they will not tell anybody. For example, we know during the Falkland War, the Argentina Navy still used the Enigma machine. And you can understand why the British won the war. So which means the British knows everything the Argentina Navy was doing. The reason I know this is because I went to, in 2019, I went to Brazil to give a talk. So the guy who invited me is Professor Tereda. He's a Brazilian Japanese. And he said during the Falkland War, the Navy of Argentina called the Brazilian Department of Defense, asked him, is the Enigma machine okay? And then the Department of Defense asked Professor Tereda. Professor Tereda was screaming at them, saying, you stupid idiots, you know, how, I mean, this was broken in 1940s by the British, you are still using it. So the point I want to make here is that really government keep those things secret for a long time. Okay. Anyway, so now I would like to go to real topics I would like to cover today, which is a public key cryptography. Why do we want to do public key cryptography? And this is because we start to have large computer networks in 1960s. That means each computer want to talk to another computer, they must have a prior key exchanges. It becomes very costly process. So with the traditional symmetric cryptography, we cannot build secure networks. So we must find a solution. So that's the fundamental motivation. So here I will really repeat. The reason we develop new public key cryptography is because we want to solve the secure communication problem over large computer networks. In particular, efficient key exchange, key agreement. Okay, the idea of public cryptography was first proposed by Diffie and Hellman. And these are two guys, okay? The guy in there, long hair is Hellman. Other one is, the long hair is Diffie, the other one is Hellman. And they won Turing Prize in 2016. The people who invent the first public key crypto system are RSA. And the left, on the left is Revest, in the middle is Shamir, and then on the right is Edelman. They invented this in 1970s in your neighborhood in MIT. Okay, and so what is the mathematical idea behind the first public key crypto system, which is the RSA crypto? And the idea is very simple. We know in general, given two large prime lines P and Q, it's very easy to multiply them to get a new number integer n, which is P times Q, like 15 equals 3 times 5. But it's very difficult to factor it. So this is the integer factorization problem. Okay, and again, what they did is use this idea to build public key cryptography. So I will give a brief introduction here about how it works. Okay, again, the idea was proposed in 1970s, and the idea is asymmetric, meaning you have two sets of keys. Okay, one is called a public key. In the case of RSA, the public keys are given by two numbers. First, this number n, which is the product of two large prime numbers, p and q, and another number r. R should be co-prime with p minus 1 times q minus 1. This is the older number of n. Okay, and the private key should be d or pq. It doesn't matter. The key point is that d times r should equal to 1 mod p minus 1 times q minus 1. Okay, meaning if I want to use it, I will make n and r public, and I will keep d secret. Okay, so but in order to achieve d, you must know p minus 1, q minus 1. Therefore, you have to know pq. Okay, now let's see how to do encryption. Okay, so what do? We choose a random number, and then we compute m to the r mod n, and then we derive number e. And E is the encrypted message of message M. Okay, and if I have the N and R, I will publish it. So anybody can send me M. Send me E. Anybody who wants to send me a message M can compute E. Then once I receive the message, only I who knows D can recover it because I compute M, which is equal to E to the D's power. Okay, from a simple number theory, we know this is true. Okay, and here the key point is that if one knows how to factor n, then one knows pq, then one knows p minus 1 times q minus 1, then one can calculate d easily and defeat the system. Okay, so the security relies on the hardness of integer factorization. So this is the fundamental idea behind RSA. Okay. Then once this is invented, the internet appears, and then we also realize as an even more important in some sense, which is authentication, which means on the internet, we don't know who you are. When for example, somebody sent a message by email, it's possible somebody pretend to be, for example, Jeffrey Arthur sending me an email. So we have to solve a problem called authentication. Okay, and so in the digital world, we use the same idea, public cryptography, and then we invent something called digital signature. And this solves the problem of authentication, which means we can use digital signature to verify if a message from Arthur or not, from Jeffrey or not. Okay, this is actually used even more. Okay, so the digital signature is to authenticate a message or transaction, and the public key is to verify. Okay, since it's public, anybody can verify. The private key is used to sign the message. Okay, so now with these things, we can do secure communication on a large network. And this is why we could build internet. Without the public cryptography, we will not have internet. Okay, so here, one thing I would like to remind you is that the public key encryption was never used for sending information. It's always used sending keys, meaning RSA is mostly used to build shared keys. Afterwards, again, we have to use the traditional cryptography, which is a symmetric crypto system to do encryption, decryption. Why? Because RSA is way too slow. Okay, so the protocol we use to assert keys now is SSL, TLS. This public crypto system allow us to send information securely. For example, your credit card. When you do online shopping, when you log into your Gmail account, and so on. Okay, and this is just an example. Okay, so we know we use a Windows system a lot. For Windows, if you use a lot, you must have to do something called update. So update basically is replace your operating system with a newer version. And one key important is how do you know the update is from Microsoft, not from somebody who is malicious, including virus inside. The reason we know is because Microsoft actually announced its public key and then signed the software. And so therefore, we can verify the software is indeed from Microsoft, not from a malicious party. Okay, and for those of you who played computer before, and you can see this. And most line is hidden behind, run behind a scene. Okay, and this is the example. So this is a number with 2048 bits. Okay, 700 digits. And this is a number Microsoft used to update the software for Windows XP systems. Namely, when you receive that software update package, there's a signature attached to it. And then you use this number to verify it's indeed from Microsoft or not. Okay. And it's based on digital signatures from RSA. And you can imagine if someone smart enough can factor this number, how much damage it can do. It can basically wipe out our whole computer system, all the Windows. Suppose you send a virus or a command like wipe out your hard drive. And if you can sign it, then every computer will performs this command and then wipe out your hardware. Anyway, so this digital signature is used everywhere now. For example, for software data, I said, for legal documents, even for voting, and so on. So we are really living in a world where we trust the God of mathematics. So what I wrote here is, in the God of math we trust. And this is a sentence I copied from the US dollars, $10 bills. In God we trust. So we're living in a very interesting era, and mathematics become the very center of our life. Okay. And for those of you who are a little bit interested in Bitcoins, and you should know, and Bitcoin is nothing but a decentralized ledger. Okay. And the fundamental idea behind is digital signature. There's no encryption there. Okay. So the Bitcoin, in the Bitcoin says anybody can join, anybody and can build a node and so on to make a copy of this ledger. Okay. The fundamental building block behind is first is the ECDSA, which is an elliptic curve digital signature algorithm. Another one is a hash function. So when you use ECDSA, the public key is used to verify, used to receive the Bitcoins, and also used to verify if a transaction is valid or not. The private key is used to send Bitcoin to other people, okay? And only legitimate user can spend. Okay, a hash function is used for POW, proof of work. And this is to synchronize the decentralized system, okay? So that's the basic behind the idea behind. And because it's built on crypto algorithm, so that's why it's called cryptocurrency, okay? The next one is, I'm going to talk about the threat of a quantum computer. Okay, the idea of a quantum computer was invented a long time ago. And one of the key guys is Richard Feynman, and I think many people must know him. I mean, he's a Nobel Prize winner, and he has a very interesting book about his life. Okay, anyway, even though they invented this quantum computer idea, but we never really find a practical use for it until 1995. Okay, and Peter Shor, who is again in your neighborhood in MIT, he invented a new quantum algorithm for factoring and to solve the discrete logarithm problems. Okay, and at the beginning, people don't care too much. For example, for me also, I say, can we build a quantum computer? Yes, we could, because in year 2000, and this guy Isaac Chuang, who is also in you guys' neighborhood, he's a professor now at MIT. He spent $15 million to show 15 equal to 3 times 5. The key is that he built a quantum computer with 7 qubits and performs Shor's algorithm. So to make it work, it really becomes scaling, but he did a proof of concept. So that's year 2000. At that time, I made a gamble. I found this work to be super interesting. So I said, I want to do this, meaning I would like to do new cryptography that can resist quantum computer attacks. Because as I said earlier, the public cryptography we used are two kinds. One is elliptic curve cryptography and an RSA. And they are based on the hardness of integer factorization and discrete logarithm problem. But they're all gone if you have a powerful, scalable quantum computer. So I gambled my career. I just decided to switch completely to cryptography research. Okay, so this new area now has a name called post-quantum cryptography. Namely, we would like to develop public key crypto system that could resist future quantum computer attacks. Okay, so that's it. Okay, so I started working in this area in year 2000. Actually, this is after I got a tenure. Okay, so I have nothing to worry about in some way. And so for the first 10 years, not much people paid attention to it, but everything changed in year 2015. This is August 2015. And this is a web page I copied at the time. Okay, I took a picture of it because in August 2015, NSA, National Security Agency, announced they will do post-quantum cryptography. Okay, for those of you interested, you should read this sentence below the background. I read it, right? The sentence is IAD will initiate a transition to quantum resistant algorithm in the not too distant future. So what is IAD? IAD is a division in NSA, it is Information Assurance Division. Okay, so here quantum resistant algorithm is exactly same as what I call post-quantum cryptography, which means develop a new cryptographic algorithm that can resist quantum computer attacks. So this is the year 2015. In the US, if you want to make a new security standard, it's actually not done by NSA, it's done by NIST, NIST, National Institute of Standards and Technology. Okay, this is a division and the Department of Commerce. So in December 2016, in the post-quantum cryptography conference, NIST announced that they will make next generation standard. Okay, and so these are related publications, and you can see they will disallow ECDSA, ISA, etc. Okay, and as I said before, so in post-quantum cryptography, we have basically two needs. Number one is key exchange. This is for secure communication. Number two is for authentication, and we use a signature for that. So this is exactly what NIST called for. The NIST called for two things. One is called CAM, but basically is key exchange mechanisms, and another one is digital signature. So the deadline for initial calling is November 2017. We already went to 3 rounds. Okay, at the moment there are 4 key exchange algorithm and 3 digital signatures as a finalist in the 3 round. And Rainbow is one of the 3 digital signature is designed by the team led by me. Okay, so this is what is going on. And actually, NIST announced they will announce the result at the end of March, but somehow they're a little bit delayed. So I expect in the next 1 or 2 weeks, we should have the first batch of standards coming out. So I don't know what the result will be. I think this is something people should be excited about. Okay, so this is what is going on with this. Okay, and so for asking what are the basic ideas behind post-quantum cryptography? So there are 5 families of post-quantum crypto systems. Number 1 is called the code-based crypto systems, and here we use a series of error-correcting code. And the second one is hash-based signatures. So here we use hash function to build the signatures. And then there's isogeny-based crypto system. So here we use isogeny of elliptic curves, and then lattice-based crypto systems. Okay, this is of course related to modular forms and the geometry of numbers. And another one is multivariate crypto system. This is based on algebra geometry. You can see this is all based on fundamental mathematics theory. Okay. So key exchange. Okay, so achieve key exchange, there are actually 2 different ways. One is use RSA explained, but there's another one even more interesting is done by Diffie-Hellman. Okay, and today, so I will give a talk about how to build secure key exchange directly based on Diffie-Hellman. Okay, so this is the main topic I'll deal with. Here, would ask me what's the difference between using RSA and Diffie-Hellman to do key exchange. Turns out it has something very fundamental going on. Okay, so this is related to what is called forward security. Meaning, if you use RSA to do key exchange, If someday somebody broke your system, then they can read every single message you sent before. Okay. But if you use Diffie-Hellman and do it every time, use different random numbers, then Diffie-Hellman guarantees that even if you steal my secret this time, it will not expose anything happened before. This is what is called forward security. So Diffie-Hellman actually give a better forward security. And you would ask me why this is important. And we learned this importance actually from someone called Snowden. I think you guys must heard of him. Okay, so Snowden actually tells us the US government is actually recording everything we send over the internet. Suppose I talk to Jeffy, use my RSA public key encryptions. Suppose they record everything we talked about before. If one day in the future, they break the RSA system and they can come back, look at the recorded message, can read everything I talked with Jeff before. I don't think this is something we like. So after Snowden's story, forward security becomes a very strong concern. So people actually like the idea of Diffie-Hellman. Okay, so now I'll start to talk about Diffie-Hellman. Okay, this is something very, very simple, I think. The Diffie-Hellman idea is very simple. So let's choose a large prime number P. Okay, and then everything is calculated mod P. Then we randomly choose a number G. Okay, and the P and G are public, which means everybody can see. Then we have Alice and Bob want to share the secret key. So what Alice will do is choose a random number A, integer, of course, and then Alice will compute G to the A and send to Bob. And Bob will choose a secret B and compute G to the B and send to the Alice. Okay, and let me repeat here, the P, the prime number, the modular is public. G is public. G to the A is public. G to the B public. But after exchange, Alice will compute G to the B to the A because Alice has A. And Bob will compute G to the A to the B because Bob has B. And then they get a shared secret because we know this is G equal to A times B. And this is the famous Diffie-Hellman key exchange protocol. Okay. To break this system, essentially you have to do what is called discrete log, meaning you have to either figure out the A or figure out B in order to get the G to the AB. Okay, so this is the Diffie-Hellman key exchange. So I would like to stop here a second. Actually, I would ask you guys, is it clear how it works?
So where's the P?
P is modular, is a larger prime number. So it's discrete. If you choose integers, if you choose G and B to integers, there's no modular operations. Then this system can be easily broken because this computer log is easy. So those numbers all compute model P. I didn't write down here. So G, basically, I choose G coming from the modular P group. So which means we work in the group, in the integers module P. Yeah, the ZP group, multiplicator group ZP.
Great.
ZP star, or you call ZP star. No zeros. The former group. Yeah, you choose random element G, and all the computation are done in this group. Yeah, is this clear? So therefore, to defeat the system, you have to do what is called discrete log, not just log itself.
Mm-hmm.
Log is easy. Okay, is this clear? Or any question or anything?
Are there any other questions?
Okay, so if not, then let's go on. Okay, let's look at it. Why Diffie-Hellman would work is because we have two functions. One is fx to the x to the 8th power, another function hx to the x to the bth power, and the commute and the composition. which means F composed with H is equal to H composed with F. Of course, here we want F and H to be nonlinear, otherwise it can be easily broken. Okay, and many people try to generalize Diffie-Hellman idea to build a new Diffie-Hellman. For example, some people use braided groups and etc. They're all completely broken. So in year 2000, I want to do post-quantum cryptography, and I look at Diffie-Hellman. I say, hey, let me try to do some new Diffie-Hellman, such that it cannot be easily broken by Shor's algorithm. So this is where I start from. Okay, this is my starting point. Okay, so that's year 2000. Yeah, and I spent 5 years working on it, and at the end of the 5th year, I give up because I happened to see a paper by Joseph Ritt, written in 1923. So Jeffrey, do you know him, Joseph Ritt? Have you heard of his name?
No, I don't know this.
So he is a professor. He was a professor at Columbia. Okay, he was the department head and so on. So he was a contemporary of Fatou and Juliet, the Juliet set. Okay, those people will study dynamic system. They study composition of functions. Okay, yeah, and then in 1923 he wrote a paper. Okay, and this paper with a title called what's the title? Sorry, I have this. The title's name is Mutable Rational Function. Okay, good. They were studying polynomials over complex plane rational functions, the commute and the compositions. Okay, so they were studying it, including Fatou and so on. Okay, and Joseph Ritt wrote a paper. He proved that if these two maps permute and the composition, if they're non-trivial, there are only 3 kinds. Number 1, power polynomials, which I showed you guys earlier, x to the a, x to the b. Number 2, Chebyshev polynomials. Number 3, rational functions coming from elliptic curve, and nothing else. So here you ask me, what do you mean by non-trivial? Non-trivial, I mean the following. There are easy way to build polynomial maps or rational maps commute and the composition, which means you just pick up a random function f, it composes itself many times. Again, it composes itself many times. And you can easily make 2 maps commute and the composition. So if you exclude that kind, Joseph Ritt proved that you have only these 3 choices. So I saw this paper, my heart was broken. So what I realized that no, I cannot generalize Diffie-Hellman, because the probable map is exactly Diffie-Hellman. Chebyshev polynomial is also the same. Chebyshev, you can understand you are building a permutation map on the unit circle in some way. And the elliptic curve, we already used ECDSA, elliptic curve digital signature. So all these are known. And Joseph Ritt seemed to tell me there's nothing else you can do. So all the system, if you use these ideas, they can all be broken by Shor's algorithm, because Shor's algorithm works on any group. So for me, since I actually thought quite a lot about this. I think, Jeffrey, you know, quantum groups, in quantum group theory, there's some very similar parallel structures. Like you have quantum affine algebra on rational functions, and then you have trigonometric generalization, and then you have elliptic curve generalization. I mean, you know this, right, Jeff?
Yes, I was going to ask about the quantum generalization. Yeah.
Yes.
Yes.
So it's very similar. Something fundamental happening here. I don't understand this. I mean, this is some topic I would like to see, maybe related to physics and so on. I don't know. So I was shocked when I saw this. I'm very surprised this result is not written in our textbook. Okay, so this is a picture of Joseph Ritt. So he was born in 1893 and died in 1951. Okay, he was at Columbia University. Okay, and this is his paper, the front page, permutable rational functions, and you can easily find it. Very fascinating for me. So, but I had a PhD student working with me on this. We were very upset because it tells me there's nothing you can do. Because you need permutable rational functions. And they're telling me the only possible construction is the Diffie-Hellman itself, or Diffie-Hellman, or this one based on championship polynomial. But this, you can understand it, some kind of unit group structure. So this is actually very interesting, right? This is you can understand that the power map polynomial basically is a homomorphism on the punctual plane, complex plane, punctual complex, and championship is on the unit circle, and then elliptic curve. That's it. So I give up. So in year 2005, I give up. I don't think we can do post-quantum exchange. Okay, and things changed after in 2007. So Jeffrey said earlier that the LWE was invented in 2005, but I heard about it in 2007. And once I heard about it, then I realized that I have a chance. So I realized maybe we can do something about it. The basic idea is add small noise, or we can call perturbation. Okay. So what I would like to do is build a Diffie-Hellman based on matrices. So we know you have a 3 matrices modeled together. You can multiply on the left first or multiply on the right first. They commute, but you cannot use this to build a key exchange because they're linear system, can be easily broken. But the LWE idea is that let's add noise to the system and somehow build a crypto system. Okay, so this is the basic idea. Okay. And so here I would emphasize, even though we call the new public cryptography invented by Diffie-Hellman and so on, it turns out in England, there's so-called GCHQ. This is basically English version of RSA. And they actually discover the IA system and the Diffie-Hellman system and the public crypto system even 10 years ahead. For example, James Ellis is a guy who proposed the idea of public key cryptography. He called non-secret encryption, and he did it in 1969, and we only really know about it in 1990s. Okay, and then there's the guy called Clifford Cox. He invented ISA, and then Malcolm Williamson invented Diffie-Hellman in 1973. So they are ahead, but we only heard about them recently.
But okay, why did we only know recently?
Because they were working for ISA of England. Their work has to be kept secret. Yes. They don't tell us what they do.
But once Diffie-Hellman was made public, then why keep the secret?
They don't want to know. I guess they don't want people to know they are working on this. I mean, right? In Second World War, they broke the German Enigma machine, but they kept it secret until 1990s, even later. And we heard about rumors in 1980s. We started hearing rumors about in the 1980s. So as I said, I mean, the Argentina Navy even used it in 1980s during the Falkland War, the Enigma machine. So this is the game of cryptography played by government. But anyway, so here I would like to say some story about James Ellis. The reason James Ellis invented this new public key cryptography idea was partially inspired by a paper shared by US in World War II by somebody from Bell Lab. We don't know who that is. People believe it's Shannon. I have no idea. So they propose a very interesting idea. So it's very simple, which is in a communication channel, I intentionally add noise such that only when somebody sends the information over this channel, because I add the noise, I know how to denoise it, only I can extract the information. This is very much the basic idea related to public key cryptography, even LWE. Okay, and you will see that when I explain to what it's about. Okay, so this is a very interesting history. Yeah, and this is James Ellis. Okay, and now I want to introduce the LWE, and then I will introduce the new post-quantum key exchange I invented in year 2011. Okay, so let me first tell you the idea of LWE, learning with the error problem. Okay, and this is as Jeffrey said earlier, was invented by Regev Order. Okay, and the problem is very simple. Okay, so first we work over ZQ. So all these numbers, everything is over ZQ. Okay, so this is a mathematical problem. Okay, you are given B as a vector B. You are given the vector A. Okay, and your job is to find S1 to Sn such that the E1 to EM follow a discrete Gaussian distribution over ZQ. So here I would emphasize ZQ is Q is, for example, choose a prime number, and we do not choose the representative to be 0 to Q minus 1. Instead, we choose minus Q minus 1 over 2, and then to what? Q minus 1 over 2. Okay, so symmetric representation of ZQ. Okay, so now let me introduce the problem very easily from physics point of view. Okay, just ignore what I wrote here. Namely, suppose we know there's some kind of linear relations, okay, in some physical systems. Then we have some measurement, okay, and B is the measurement result. AIJs are the parameters related, for example, temperature, pressure, and so on. And I want to find linear relation between B and the other side. So, but we know our hands are shaking. Maybe we had too much drink the night before, so we always make errors. So in reality, we're solving such a problem in physics, always, in order to find S1 to Sm, which means in order to find the slope. But here, the only difference is what? We're not working on real numbers. We're working on mod Q. So this is the learning with error problem. Okay, I would like to stop a little bit here. And here, of course, let me repeat. So what is discrete Gaussian? Basically, you are doing a Gaussian and you are doing a Gaussian distribution, and then at each integer, and you choose this value, and then you normalize it. Okay, with of course with certain standard deviations. And namely, this most of the time the values are chosen small, near 0, and then very small chance that they choose off 0. So that's the discrete Gaussian definition. I'll stop here for a second. Is it clear what the definition of the problem is? So the key is what we know B, the vector B, and we know the matrix A. Okay, your job is find the vector S, such that afterwards the difference E1 to EM, the vector E, follows discrete Gaussian.
Are you going to choose Q very large?
Q not so large, no. For example, 10,000 or 100,000, a prime number. The large is N. N should be 1,000, 500 to 1,000. Q should be N squared or something like that.
Mm-hmm.
Okay, and the standard deviation of this like square root of N. Okay. You have to choose the parameter carefully. Okay, so N is the key number. Q depends on N. The standard deviation depends on N. Only if they satisfy a certain condition. So what Regev did is that he proved that if you can solve this problem, you can solve what is called approximate shortest vector problem. Not to find the shortest vector, to find the approximate shortest vector, which means a constant polynomial of N times the shortest vector. If you can find a vector the length of that one, you defeat the system. You can find the solution. That's why it's related to lattice, what is called a lattice cryptography. So how do you create this problem? It's very simple. You first choose S1 to Sn. Okay, this is a fixed, and then you can choose the row vectors AI as many as you want. Okay, randomly, and then you compute it, and then you add a small error to it. And in the end, you can produce this matrix, and you give me the problem. And this problem is learning with error problem. But discrete, everything mod Q. Okay, so what the Regev, let me repeat. What the Regev proved is that if you can solve this problem, you can solve a short vector problem of a random lattice. And this is not the shortest one, okay? It's called approximate shortest vector problem. As not meaning if you find a vector short enough in some lattice, then you defeat this problem. So this is learning with error problem. I would like to stop here a second. And you guys should know this. I mean, this is nothing super fancy, right? As I said, from physicist's point of view, this is very simple. This e's are coming from measuring errors. And otherwise, what you're supposed to do is find a linear relation between certain parameters. And you can solve linear system easily, find the S, if you don't have errors. But we always, of course, I mean, you guys all know, if those errors form a normal distribution, and then we have a way to solve it, which is what? Called the least square method. We can easily find a very near solution for S1 to S. Okay.
So now you'll tell us RLWE.
Yes. Next one is I will tell you what RLWE, and I use it as an example to explain to you what a ring key exchange is. So in the case of RLWE, we choose n to be power of 2, and q equal to 1 mod 2n. Okay. And it's a prime number. We define the ring. RQ is ZQX mod x to the m plus 1. Okay. Now I give you the RLWE problem, which is in the RLWE, you are given this element B, you are given an element A, and you are supposed to find S, such that B equal to A times S plus E. And E is an element in this ring. And this ring, every element can be expanded into polynomials, which means I want each coefficient of E follows the discrete Gaussian independently. That's the ring LWE problem. Is this clear or not? So how to construct it? It's very interesting. You randomly choose A, you randomly choose S, and you try to randomly choose this E. Of course, let me repeat, inside E, each coefficient follow the discrete Gaussian. Okay, and then you compute AS plus E, and then you produce B. Then I give you B and A. Your job is find the S. Okay, this is the ring LWE problem. Okay, of course, you would say, yeah, if you give me only one, you can solve it easily. You're right, but normally we give you a few samples, which means I choose the same secret. I give you B1, A1, and then B2, A2, and you find the same solution as. Okay, then people can prove that to solve this problem, you have to solve an approximate shortest vector over what is called ideal lattice, not a random lattice. Okay, and you ask me, why do you want to do ring LWE? Because we want to have a system more efficient in terms of computation and the key sizes. And if you can solve LWE, you can definitely solve ring LWE, not the other way around. Okay, so this is a much simpler version in some way with structures inside. But this is more efficient because we reduce the key size. Instead of remember a matrix, we only remember polynomial. Okay, is it clear what the ring LWE is?
Yes.
Okay, very good. Now I'm ready to do the Diffie-Hellman from ideal lattice. Okay. So what we do is we fix a ring. Okay, we choose Q properly. We choose the standard deviation of the discrete Gaussian properly, and so on. Now we use what is called normalized version learning with error problem. Okay, so here A is public. Okay, A is public. Okay, and Alice were given A and the ring is public. Okay, the parameters are public. Mod Q, the Q is public. Yeah. So what Alice will do, Alice will choose a secret SA and a secret EA. So here, this is called a normalized version, which means my SA also follows normal distribution and follows Gaussian distribution. Same distribution as the error. But here I will multiply 2 on EA. But here everything is mod Q, okay? This is very important. Everything is mod Q. And Bob is computed PB equal to A times SB plus 2EB. And these two operations are almost like Alice computed G to the A, Bob is computed G to the B. Okay, so this is the first step. And then the exchange. After exchange, Alice will use PB multiplied by its own secret SA and then add 2 times GA prime. This is a new error term to add. And Bob does almost the same, but add 2EB prime. And if you look at them, here A follows a uniform distribution, which means every single entry A is choose uniformly randomly. Okay, if you look at these two sides, realize the central part is A times SA times SB, and they are equal, and those terms are small. Therefore, these two values are very close, but they are not exactly equal. They differ by 2 times something. Okay. Yeah, and from naive point of view, that's it. You can do a key exchange, right? You just mod 2. Yeah, because then you each combination give you 1 bit. You get a share the secret. No, but you cannot do that. Okay, why? And the reason is very simple. Okay, you can see that, as I explained to you before, naive way says that if you choose Q to be 17, and then if you have 2 numbers, if you differ by 2 times something, then if the even numbers remain even number, odd number remain odd number. That's definitely the case. Okay, let's look at if you use representation coming from -8 to 8, and then the what? You can see these 2 numbers now, even though it's the same value, but you break the what? The parity. Okay, the parity of even and odd disappeared. You would ask me why? Why this happened? Okay, and the explanation is very simple. Okay, so you can see that suppose I have a value near the boundary, which means I have a value near -q-1/2 and a q-2, and it's possible one error jump to the left, another error jump to the left. And that means one side will do 1 more time mod q from the other side. Therefore, the parity is broken. So therefore, you will not get the same value. But if you are in the upper half region, okay, if one error jump 2 points and another error jump up and down, but doesn't matter because if none of them will cause additional modular q operations. So therefore, we cannot naively, let me repeat, here we cannot naively just do a modular Q2 operations to achieve the same keys. So now comes my idea to do this. Okay. So I will just use this map to explain. So once you get these 2 values, Ka and Kb, okay, Ka and Kb, and then one side will send the signal at the other side, which means I'll look at each coefficient of my polynomial. If it's in the upper half region, which is if the value is between -q/4 to q/4, I'll send a 0 to the other side. If the value is between at the lower region, okay, then I'll send a 1 to the other side. Okay, and after that, what we'll do is the following way. Both sides, if the signal is 0, then we just do modular 2 operations. And if the signal is 1, we both sides add q-1/2. Then we do modular 2 operations. Why this works? Because once you add q-2, you switch the bottom half to the top half to the bottom half. Then when you add the small errors, you will not cross the boundary, and then it will not cause any additional modular co-operations. Therefore, it maintains the parity, which means even, and if you add a small error times 2, and the even will be even, odd will be odd. Therefore, you achieve the same keys. And this is the new LWE-based key exchange. And that's the main part. Okay? So the most important thing I invented is this signal function. Okay, and that's it. Yeah. So I will stop here for a second. I hope this is understandable to you how it works.
So this is purely classical. Does it relate to quantum?
No, this is pure classical. So post-quantum cryptography, we are using mathematics to build the crypto systems which claims that quantum computer cannot break. There doesn't exist any efficient quantum algorithm to break it. So everything is pure classical. No, in post-quantum cryptography, we only do classical. We don't do quantum physics models. Of course, when we do cryptanalysis, we'll analyze if Ponton algorithm can be used to make it efficient.
Very interesting.
Yeah, so this is the, so let me go back to the formula. This is the one I invented in 2011. The first post-quantum key exchange, which tried to imitate Diffie-Hellman. Of course, it's slightly different from Diffie-Hellman. When in the Diffie-Hellman case, when you exchange information, you don't have to do anything. Here, you do one more step. Let me repeat. Either Bob or Alice, doesn't matter, care. Only one side is allowed to do one more step. Send a signal function to the other side, which means we're looking at Ka, Kb, and look at each coefficient. And if it's the upper half region, we send a 0, and lower half region, we send a 1. So which means I send a vector to the other side with zeros and ones. That's all. And afterwards, we can get the shared keys. That's it. That's the key invention I did. And the most important idea is the signal function idea, and which facilitates us to achieve the same key on both sides, with high probability, of course. So namely, as long as these errors are less than Q/8, those error terms, SA times EB and 2EA, and then it's okay. We're guaranteed. So by adjusting parameters, we can control the probability, the failure probability to a minimum. For example, we can either make it 2 to the minus 60 or 2 to the minus 100, whatever. And the key idea is after exchange information, you send one more signal function to the other side. Only one side.
So is that the end of your talk?
Oh, no, not yet. I have a little bit more, but this is, I mean, I would let people ask questions. And this is, I think, the most interesting part of the talk. So I pause for a second. I mean, I should finish quickly, but not end. No. Any questions, anything? Oh, if not, then let me go continue, okay? So if you want to write down clear formula, this is what I wrote here. So you introduce a new signal functions and so on. So this is just a mathematical formula to describe what to do. Okay, so this is definitely signal function and how to get the keys, and then we can improve everything. Okay, so that's it. Okay, so the key derivations and so on. So in the end, it's a modulo 2, and you get a polynomial with 0, 1 coefficients, and that's the shared keys. Okay, so that's it. So my paper, so this invention was done in 2011, and my paper was posted online in 2012. Later, a few people followed. For example, there's a paper written by Chris Pikert in 2014, and he claimed he invented new. He claimed he did the same thing. He claimed he invented a new algorithm, and his signal function is the one on the right, and my signal function is on the left. Okay. And he claimed he invented a new thing. Of course, I disagree. I mean, this is for me is a simple variant of what I did. Okay. And then somebody did it, and so on and so on. And there's in 2015, there's something called New Hope, which is based on what Piker did, and they claimed to invent a new thing. And then Google actually used it, and then they stopped it. We had a negotiation in some form, and I believe they infringed on my patent. What they did, Google did. Okay, but anyway, that's not the main point. So I want to say is that there's a difference between what I invented, other guy invented, and I claim that this is just a simple variant of what I did, and just make it more precise or something. That's all. Okay, and then let me continue to try to finish this talk. So what I want to say is that we can also easily prove that if you can defeat my system, then you can solve an LWE problem. Okay, so they achieve what is called a provable security. Okay, so this talk, the part about key exchange is done, but here I would emphasize lattice-based crypto systems has broad applications in something called a fully homomorphic encryption, okay, which allows us to do computation of encrypted data, but the main issue, of course, is efficiency, okay? So lattice cryptography is a very interesting topic. And so we are really now moving to a new era. I think in the next few days, as I said before, the NIST will announce the result about next generation standard I think we all should pay attention. And often people ask me, will Bitcoin be okay after no, my answer is no. Bitcoin will be finished. Okay, but anyway, I would emphasize that now cryptography is really needed area to protect us. Okay, but in principle, authentication and also protection, integration of data and so on is very important. Okay, but of course, efficiency is a concern. Normally, the post-quantum system is a little bit less efficient and so on. Okay, for key sizes or computation. Computation is actually more efficient. Often is the key size of the problem. Okay, so I'll make a quick summary. So cryptography is now used everywhere, and privacy interesting concern. And for us, we are mathematicians. I think there's a good future for mathematics in cryptography. Since I'm now working in BINSA, I would like to make an advertisement for BINSA. So BINSA stands for Beijing Institute of Mathematics Science Applications. So I built a lab on privacy protection and blockchain securities. And we're basically doing public work using mathematics to develop new public ideas for cryptography, for blockchain, and so on. So this is what we do. If you're interested, let me know. And we are always looking for good people. Okay. And I think that's pretty much what I will talk today. I think I'm actually running out of time already. And thank you guys again very much for listening to the talk. So I'll be happy to take some questions.
Thank you, Jintai Ding, for a really interesting talk.
Thanks.
Many things that we didn't know before. So I'm going to stop your sharing so we can see the audience. And
sure.
When you ask a question, turn on your video so we can see your face. Who would like to start? Kaifeng, did you have a question?
Yeah, so very nice talk. And my first question is to against the quantum algorithm or quantum computation, what's the hardness of the problem you use, like the shortest lattice vector?
So no, here is not the shortest vector. It's approximate shortest vector.
Yeah, like what's the hardness of the approximate shortest vector?
So for now, we don't know any efficient quantum algorithm to defeat it.
I mean,
what we can prove now. So in terms of, so here maybe I would explain it about proof security. In cryptography, when somebody says something to prove secure, we don't prove it secure. We prove that if you can defeat the system, you can solve a hard mathematical problem. So in this case, what we can prove is that if you have a quantum algorithm that can defeat LWE problem, then this quantum algorithm should be able to solve what is called approximate shortest vector problem. As for how hard it is for quantum algorithm to solve that, we don't really know. We believe. Or something.
My question is what's the complexity class? That's this problem.
We don't really know. We don't really know.
Okay, I see. And also you mentioned the privacy. So there's a concept called differential privacy. Can differential privacy also be used for post-quantum cryptography?
The differential privacy is different. I think differential privacy is mostly referring to a problem by adding a little bit of noise, but this case not a modular. It's in the on the real data, on the real number, you add a noise, try to hide your identity. No, this is different. But there's another topic related to privacy called the multi-party competition. Yes, in multi-party competition, for example, you use Diffie-Hellman algorithm and so on. There's also post-quantum concerns.
Oh, I see. Yeah, thank you.
You're welcome.
So are there other questions or comments? I see your colleague Tsinghua from BIMSA is here.
Oh, yes.
Hi, Tsinghua.
Hi, sir.
Do you have any comment on this beautiful talk?
It's a good talk. It's very beautiful.
Oh, thank you. So anyone, any question? But anyway, so maybe I want to make one more comment. So if you're interested in topic, you should Google NIST and PQC. You will find tons of information about the standardization process, new attacks, and so on. So this is a very interesting topic. We have a lot of arguments, very furious fighting and so on, different opinions and so on. It's very interesting.
And when will the NIST announcement come out?
They were supposed to be end of March. So I think this guy, Dan Bernstein, made a joke. He said March 40th or something. So I expect to be very near. I expect to be very, in the next 1 or 2 weeks at the most, I think. Yeah, from what I heard, mostly, in this kind of things is very serious, very important. So there should be lawyers' approval. When they are lawyers, then things are always slowed down. Yeah.
So what's next?
The next, I think it will be, because we're not sure actually. For example, there's one thing very interesting. For example, so I work a lot also on multivariate crypto systems, and there's a new attack on my Rainbow and so on. So there's a very interesting phenomenon, for example, okay? In lattice cryptography, the most important tools attack a lattice system is called lattice reduction. I think you must have heard of it, because there's a famous LLL reduction, okay? So there's a very interesting story about LLL reduction. Okay, LLL reduction is an algorithm given by Lovash, Landstrom, yeah? And then we have a theoretical estimate about how good it is, which means we have a theoretical estimate how short the vector should be from number 3. But if you do experiment, it's always much, much better.
Oh.
And we have no idea why. So this is something, if somebody can explain that very well, it's very important, because we're very worried, because, if somebody finds some new idea, explain why, maybe they can improve the attack algorithm much more efficiently, then we're in trouble. Okay, so this is the one thing. And concerning the earlier question, about the complexity class and so on, how efficient the quantum algorithm can solve problem, we actually know relatively little. Okay, about it. So there are tremendous progress made in the last few years, because standardization process, really, if you do good work, you can become famous and so on. So people really are driven to work on it. So, but I think this area is a very, very promising area for the future research, for future application. So let me repeat, okay? Right now, for example, when we give this talk, when we next connect to the Zooms, and this key exchange is used. So it's the digital signature and key use is in every transaction we do online now. That means if we decide to switch to post-quantum system, we have to change every single device, every computer. You can see there's a tremendous business opportunities there as well. But if we don't do a good job, you can imagine our information system could be interrupted. So I think this is a great area to work on, practically and theoretically. There are many interesting questions, as I said. I mean, just this paper by Joseph Ritt, I found to be fascinating. Yeah. I was really shocked. I never learned that before in the textbook.
Well, Jintai, I want to thank you for telling us so many interesting things that we didn't know before, and also giving us some new mathematical problems to worry about, so we don't have to worry about other things going on in the world. Thank you so much.
Okay, thank you again. Thank you everyone for listening. Yeah.
We'll see you next week. Bye-bye.
Okay, see you then. Okay, take care. Okay, bye-bye.
Bye-bye.